Hi, my name is Ray Jenkins. I'm a PhD student at Dartmouth College, working with Sergey Baradas and Sean Smith. And today I'm going to be talking about some tools that we've developed for analyzing, observing Zigbee home area networks. Before I go into this much further, I want to talk about our mantra at Dartmouth. In 2011, Joshua Wright, a security researcher, made this statement that security will not get better until tools for the practical exploration of the attack surface are made available. So what this means is that we need to have the tools to analyze and understand the vulnerabilities before we can go about actually fixing them. So what are these Zigbee networks? Well, Zigbee is, as you can see, a smart grid type technology in which the smart grid talks to the smart meter, which talks to devices within your home, such as automated lighting, security systems, smart appliances, and those sort of things. So those are the type of devices that we're going to be targeting, at least in this talk. An example home area network I have set up for you is we have a Harmony P2 gateway talking to several Zoe smart metering plugs. So if you come over here, we can see we have a gateway right here. This device would actually speak to your smart meter. And then we have a plug similar to this connected. This would be connected to a light or something of that nature. And the user could use this gateway to control the light, control the energy in their home in some automated fashion. So I also want to introduce our Appy Mode. So here I have an example of this. This is a PCB designed, created by Dartmouth alumni Ryan Spears. It has been extended through his company, TCIPG spinoff, Riverloop Security. This device was created specifically to fill a gap. There were no other devices on the market that had the tools that we wanted for this type of research. In addition, the devices that were out there were outdated and becoming very hard to get a hold of. So this device specifically is designed for the security research that we will be doing. Now I want to introduce Killer Bee. So Killer Bee is a software framework for exploring and exploiting Zigbee networks. It has lots of tools like eavesdropping, traffic replay, crypto systems and analysis, and so much more. Today I'm just going to talk about a simple example of what you can do with Killer Bee. Killer Bee, the software, was originally designed by Joshua Wright, who I've already mentioned. It was extended by Ryan Spears and Ricky Malgares, again with their company Riverloop Security. Now I want to start a live demo. So we'll see here, that should come up in a second. I will be running a Wireshark instance, which is receiving information from Killer Bee, which is communicating with our Appy Mode. And then we have our network that we have set up. So these devices are speaking to each other right now. Our Appy Mode will be listening to these devices quite passively and sending that mode to Killer Bee. Killer Bee will be giving that information to Wireshark. So as we see here in Wireshark, I'm getting packets that are being sent for these two devices. So I see source 4 zeros. I know that is my gateway. I also see a source of 1FB6. I also know that is the smart meter. Most of this traffic will be encrypted. However, if you had the keys, you could definitely inspect this. But this would be used for actually analyzing what is speaking on your network, what kind of traffic is going on, what devices are in the area, and what they're saying to each other. All right, so that's kind of the idea behind here. Again, this is just a simple example of what you could build on top of Killer Bee. Again, utility security personnel could use this to identify networks and the connected devices, watch the actual traffic, and look for foreign or rogue nodes communicating in the area. Now I want to introduce Isotope, which is a software toolkit for actively fingerprinting Zigbee devices, like our Appy Mode that we've introduced. Again, developed by Ryan Spears and David Dowd, currently maintained by myself and others at Dartmouth. Isotope is a framework for creating baseline fingerprints on network devices. So before I go too much further, what are these fingerprints? So Isotope works at the physical layer of the device. And as you see here, I have a standard packet, which has the preamble, start of frame delimiter, and the frame length. I'm not going to worry about the rest of it. What we're going to worry about is these first 3 sections of the packet, which we craft in various ways. I'm calling them isotopes here, to elicit a response from some device. One of the ways that we do this is to vary the length of the preamble. So, of course, the standard says that it should be 8. What happens if we change this? The standard says that the preamble should be 0s. What happens if we modify that in some way, inserting different values into the preamble? So these are our isotopes. These are packets that we will send out in some manner and look for the responses, and these responses will become characteristic of the devices. So how could you use this? Fingerprints provide additional network intelligence on what devices are running on the network. So for an example, if you have a vulnerability, you can look at the devices that are affected by that vulnerability, look at your network, identify what devices might be vulnerable, remove them, upgrade them, whatever you need to do. So network device fingerprints are already included in many IDS systems, and Isotope provides these fingerprints for those type of systems. So here's a quick animation of precisely how Isotope works. So from a machine, you would send an isotope, one of these packets, to a transmitting device that you already control. This would transmit the crafted packet to some unknown device. This unknown device may or may not respond. If it does respond, this response is picked up by a receiver, and then from the receiver we get our fingerprint. All right? So we have this circle that describes exactly where we're getting the fingerprint in this process. So how well does this actually work? Well, it works quite well, at least with the chips that we've tested on. I've listed 3 here and the different methods. So we'll see that the ChipCon chip, which is actually the one that's in the Appy Mode, it responds to variable preamble lengths, meaning if we change the preamble length from what the standard says it should be, ChipCon actually still responds, and in a characteristic way. In addition, we can see that this ATmega 128 additionally responds to a variable preamble. Through the combination of these different techniques, we can uniquely identify these different chips. There are several more chips that we haven't tested. There are some that we have that I just don't have the results for. But again, using a combination of these techniques, we can produce unique fingerprints for the physical layer. So in conclusion, what I've presented are 2 tools, Killer Bee and Isotope, for practically exploring Zigbee networks. Killer Bee has previously been used in industrial penetration tests and is currently used at some utilities. We are currently shopping Isotope with our industry partners here at TCIPG and looking to see if they can find a use for it in their organizations. If you have any questions, you can contact myself or my advisor, Sergey, at cs.dartmouth.edu. Thank you very much.